A haloalkane molecule is formed when a hydrogen atom in an alkane molecule is replaced by a halogen atom. Some typical haloalkanes are illustrated here. This class of compounds is also called alkyl halides. Haloarenes are formed when a hydrogen atom in an aromatic compound, such as benzene, is replaced by a halogen atom. These compounds are also called aryl halides. Many organic compounds that contain halogens occur naturally. Both synthetic and naturally occurring halogenated organic compounds have important uses in medicine and research. Chloramphenicol is a naturally occurring substance produced by soil microorganisms. As you can see in the structural formula, it contains 2 chlorine atoms. Chloramphenicol is used as an effective drug in the treatment for typhoid fever. The thyroid gland, a butterfly-shaped gland at the base of your neck, produces the hormone thyroxine. Notice the 4 iodine atoms in the chemical formula. A lack of dietary iodine can lead to a deficiency of this hormone, which can eventually lead to goiter. Many countries have mandated that small amounts of iodine be added to table salt to minimize the risk of goiter. Chloroquine, a synthetic compound, is used for the treatment of malaria. Halothane is used as a general anesthetic during surgery. These compounds are used in industries as solvents for relatively non-polar compounds, and also as starting material for the synthesis of a variety of organic compounds. Haloalkanes and haloarenes can be classified in several ways. One way is to classify them based on the number of halogen atoms. Chloroethane, a monohaloalkane, and chlorobenzene, a monohaloarene, each containing 1 halogen atom, are shown here. Dihaloalkanes and dihaloarenes have 2 halogen atoms in their formulae. Trihaloalkanes and trihaloarenes with 3 halogen atoms are also known to exist. Based on the hybridization of the carbon atom to which the halogen atom is bonded, monohalo compounds are classified as alkyl halides, allylic halides, benzylic halides, vinylic halides, and aryl halides. In alkyl, allyl, and benzyl halides, the halogen atom is attached to an sp3 hybridized carbon atom. On the other hand, in vinyl and aryl halides, the halogen atom is attached to an sp2 hybridized carbon atom. We'll start with the alkyl halides, or haloalkanes, which have the general formula Rx. R here represents an alkyl group. In these compounds, the halogen atom is bonded to an sp3 hybridized carbon atom. The homologous series of alkyl halides can be represented by the formula CnH2n plus 1x. based on the nature of the carbon atom to which the halogen atom is attached. The alkyl halides are further classified into primary, secondary, and tertiary. In primary alkyl halides, the halogen atom is attached to a primary carbon atom. For example, ethyl chloride is a primary alkyl halide. In secondary alkyl halides, the halogen atom is attached to a secondary carbon atom. Isopropyl chloride shown here is a secondary alkyl halide. In tertiary alkyl halides, the halogen atom is attached to a tertiary carbon atom. For example, in tertiary butyl chloride, the chlorine atom is attached to a tertiary carbon atom. You need to be able to recognize allylic carbons. Allylic carbons are carbon atoms bonded to a carbon atom that is doubly bonded to another carbon atom. As the illustrations here show, allylic carbons are one position away from a double bond. Allylic carbons are sp3 hybridized. Allylic haloalkanes have halogen atoms attached to allylic carbons. In benzylic halides, the halogen atom is bonded to a carbon atom with sp3 hybridization, that is linked to an aromatic ring. In primary benzylic halides, the carbon attached to the halogen has only one carbon-carbon bond. Here are secondary and tertiary benzylic halides. In a secondary benzylic halide, the carbon attached to the halogen atom is bonded to two other carbons. In a tertiary benzylic halide, the attaching carbon is bonded to three other carbon atoms. It will be helpful in your chemistry studies if you can identify vinylic carbons or alkenyl carbons, as they are sometimes called. Vinylic carbons are sp2 hybridized and are double bonded to one carbon atom. The vinylic carbons in two different molecules are shown in the illustrations here. Vinylic halides have a halogen atom bonded to an sp2 hybridized carbon atom of a carbon-carbon double bond. Two examples of vinylic halides are shown here. In aryl halides, the halogen atom is bonded to an sp2 hybridized carbon atom of an aromatic ring, as illustrated here. Learning the proper nomenclature of organic molecules is very important, and it takes a lot of practice. Many compounds have common names as well as systematic IUPAC names. The common names of alkyl chlorides can be found by giving the name of the alkyl group followed by the halide. In the IUPAC nomenclature system, they are named as halo-substituted hydrocarbons. Let's write the IUPAC name of the given molecule. The longest continuous carbon chain has 4 carbon atoms, and hence the root word is bute. Since the longest carbon chain is saturated, the primary suffix is -ane. Thus, the name of the parent carbon chain is butane. We then need to identify the substituent and its location. For this, we need to start numbering the carbon chain from the end nearer to the carbon atom to which the substituent is attached. We see that the carbon atom with the substituent chlorine is in position 1. Thus, the name of the given compound is 1-chlorobutane. Now try these practice problems on your own. Give the IUPAC names for these two molecules. Are they primary, secondary, or tertiary haloalkanes? The IUPAC name for the molecule on the left is 2-chloro-2-methylbutane. It is a tertiary haloalkane as the chlorine is bonded to a carbon linked to 3 other carbon atoms. The IUPAC name for the molecule on the right is 3-chlorohexane. It is a secondary haloalkane. Notice that the chlorine is bonded to a carbon linked to 2 other carbon atoms. Apply your skills in a new way. Draw the formulae for the compounds here. Try these on your own before checking the answers. The illustration on the left gives the trans isomer of 2,3-dibromobute-2-ene. Can you draw the cis isomer? Shown here is the cis isomer of 2,3-dibromobute-2-ene. The common names of haloarenes give the name of the aryl group followed by the halide. Common names may use the prefixes ortho, meta, and para to indicate relative spacing, 2, 3, or 4 carbons between the halogen atoms. In IUPAC nomenclature, haloarenes are named as substituted arenes, listing the location and type of the halogen atoms. Let's work through some practice problems together. What are the IUPAC names of these compounds? All 3 molecules are benzene derivatives. Remember that if more than one similar substituents are present, then we must give the location of each and include prefixes indicating the number present. The common and IUPAC name for molecule A is fluorobenzene. Molecule B is often called meta-dichlorobenzene. Its IUPAC name is 1,3-dichlorobenzene. The common name for molecule C is symmetrical trichlorobenzene, while its IUPAC name is 1,3,5-trichlorobenzene. Dihalogenated compounds with the same type of halogen atoms can be classified based on whether the halogen atoms are on the same or adjacent carbons. If the 2 halogen atoms are bonded to the same carbon atom, then it is called a geminal dihalide. Geminal dihalides in the common system are named alkylidene halides. In the IUPAC system, they are named 1,1-dihaloalkanes. Thus, the molecule shown here can be called ethylidene chloride. Its IUPAC name is 1,1-dichloroethane. If two halogen atoms of the same type are bonded to adjacent carbon atoms, it is called a vicinal dihalide. Vicinal dihalides in the common system are sometimes named alkaline dihalides. In the IUPAC system, they are named 1,2-dihaloalkanes. For the molecule shown here, the common name is ethylene dibromide. Its IUPAC name is 1,2-dibromoethane. Here are some additional practice problems. Try to name molecules A, B, and C on your own before proceeding. Molecule A is 1,1-dichlorocyclopentane. Molecule B is correctly named 2,4-dibromopentane. In this molecule, you will get the same name whether you start counting from the left or the right. Molecule C is 7-bromohept-1-ene. You might see this written as 7-bromo-1-heptene, using earlier IUPAC guidelines. The double bond takes priority over the halogen atom, so carbon number 1 is at the far right. Practice is the key to learning organic nomenclature. Here are 2 problems to try on your own. What are the common and IUPAC names of these compounds? Vinyl bromide and allyl chloride are the common names of these molecules. What are their IUPAC names? The common name of compound A is secondary butyl bromide, and its IUPAC name is 2-bromobutane. The common name of compound B is neopentyl bromide, and its IUPAC name is 1-bromo-2,2-dimethylpropane. The common name of compound C is tertiary butyl bromide, and its IUPAC name is 2-bromo-2-methylpropane. The IUPAC name for vinyl bromide is bromoethene. No number is necessary for the position of the bromine atom. Whichever carbon atom it is attached to must be the first carbon. The IUPAC name for allyl chloride is 3-chloropropene. Because of the double bond, the leftmost carbon is at position number 1. Let's practice another important skill. That is, drawing structural formulae from names. It is best if you start with the end of the name with the carbon backbone and work forwards. Try them independently before checking the answers. The correct structural formulae are shown here for 2-bromo-2-iodobutane and 1-fluoro-2-methyl-cyclohexene. Remember that if there is more than one substituent, they are listed alphabetically. Pure alkyl halides are colorless. For example, methyl bromide or bromomethane is a colorless gas that can be used as a pesticide. However, this use is being phased out due to its toxicity. Historically, it was used as an industrial fire extinguishing agent. Methyl bromide is also known to be an ozone-depleting chemical. The alkyl bromides and alkyl iodides may develop a color when exposed to light. For example, ethyl bromide turns yellow when exposed to light and air. Many volatile alkyl halides have a sweet smell, but this may not be noticeable unless the concentration is relatively high. Lower alkyl halides, including methyl chloride, methyl bromide and ethyl chloride, as well as some chlorofluoromethanes, are gases at room temperature. Higher alkyl halides are liquids or solids. You have already studied that the carbon-halogen bond in halogen compounds is polar. Due to the greater polarity and higher molecular mass of haloalkanes as compared to the parent hydrocarbons, the dipole-dipole and van der Waals forces of attraction are stronger in these compounds. Hence, haloalkanes have considerably higher boiling points than those of hydrocarbons of comparable molecular mass. For a given alkyl group, the boiling point increases with increasing atomic weight of the halogen. This is due to an increase in the magnitude of van der Waals forces of attraction with an increase in size and mass of the halogen atom. Thus, among the alkyl halides, alkyl iodides have the highest and alkyl fluorides have the lowest boiling points. For a given halogen, the boiling point increases with an increase in the number of carbon atoms in the chain. This is again due to the increase in the magnitude of van der Waals forces of attraction with an increase in the size of the carbon chain. The boiling points of isomeric haloalkanes decrease with an increase in branching. This is due to the fact that with an increase in branching, the molecule attains spherical shape with less surface area. This results in a decrease in the magnitude of van der Waals forces and hence the decrease in boiling point. Thus, among the isomeric butyl chlorides, the straight-chain isomer, N-butyl chloride, has the highest, while tertiary butyl chloride has the lowest boiling point. The haloalkanes are only very slightly soluble in water. Why? For a haloalkane to dissolve in water, energy is required to break the attraction between the haloalkane molecules and the hydrogen bonds between the water molecules. As new attractions between the haloalkane and water aren't nearly as strong as the original hydrogen bonds in water, less energy is released during this process. Thus, haloalkanes are sparingly soluble in water. Haloalkanes do tend to dissolve in organic solvents. The intermolecular attractions that form between haloalkanes and the solvent molecules have similar strengths as the attractions being broken in the separate haloalkane and solvent molecules. Alkyl fluorides and alkyl chlorides are less dense than water. In a mixture with water, alkyl fluorides and alkyl chlorides would be the upper layer. Alkyl bromides and alkyl iodides are denser than water. In mixtures with water, alkyl bromides and alkyl iodides would separate into the lower layer. Increasing the number of halogen atoms increases the density of the compounds. Aryl halides are polar molecules due to the presence of the polar carbon-halogen bond, but they are less polar than alkyl halides. Aryl halides have physical properties very similar to alkyl halides. We should make special note of the isomers of dihalobenzenes. If we compare the ortho, para, and meta-isomers of dichlorobenzene, we see that their boiling points are nearly the same. However, the para-isomers have higher melting points. The greater symmetry of the para-isomers fits better into the crystal lattice, making the para-isomers melt at relatively high temperatures. Aryl halides are practically insoluble in water and are denser than water. Here is a problem for you. Arrange these compounds in increasing order of their boiling points. Let's start by drawing the structure for each compound. All the three structures contain one chlorine atom. Since the boiling point increases with an increase in the number of carbon atoms, we would expect one chlorobutane with its 4 carbon atoms to have the highest boiling point. The other two compounds have 3 carbon atoms each, but one chloropropane is a straight chain, while isopropyl chloride is branched. Branched molecules have lower boiling points. So, isopropyl chloride should have the lowest boiling point. 1 chloropropane is in the middle. Haloalkanes undergo 3 types of reactions. They are nucleophilic substitution reactions, elimination reactions, and reaction with metals. Before you learn about the nucleophilic substitution reactions, get to know what a nucleophile is. The word nucleophile means nucleus seeking. Essentially, a nucleophile has an unshared pair of electrons, and it can use these electrons to make a covalent bond. Nucleophiles can be thought of as Lewis bases or electron pair donors. Nucleophiles may be anions or neutral molecules. In nucleophilic substitution reactions, a nucleophile or a Lewis base substitutes for a halogen atom in an alkyl halide. Here is the general form of the reaction. The halogen is referred to as the leaving group because it leaves the alkyl halide when the nucleophile reacts. Since the substitution reaction is initiated by a nucleophile, it is called a nucleophilic substitution reaction. Common nucleophiles include the hydroxide ion and water, both of which react with alkyl halides to make alcohols. Ammonia and substituted amines are used to convert alkyl halides into amines. Note the lone pairs on each formula. Sodium or potassium salts of alkoxides can be used to make ethers from alkyl halides. Sodium or potassium salts of carboxylates can be used to make esters from alkyl halides. Sodium iodide can be used to make alkyl iodides from alkyl halides. Lithium aluminium hydride can be used to convert alkyl halides into hydrocarbons. Some nucleophiles can be described as ambident nucleophiles. These contain two nucleophilic centers and so can link to the alkyl halide in two different ways. For example, the cyanide ion can link through the carbon atom to make alkyl cyanides. If the cyanide ion links through the nitrogen, alkyl isocyanides will form. The nitride ion is another example of an ambident nucleophile. If it links through the nitrogen, a nitroalkane will form. It can also link through the oxygen to make alkyl nitrides. Depending upon the mechanism or the reaction conditions, nucleophilic substitution reactions can be classified as SN1 or SN2 reactions. The S is for substitution and the N is for nucleophilic. Since these reactions are initiated by the nucleophile, the number gives information on the reaction kinetics, 2 for bimolecular and 1 for unimolecular. Let's start with the SN2 reaction. The reaction between 2-iodobutane and hydroxide ion to yield 2-butanol is an example of an SN2 reaction. This reaction follows second-order kinetics, meaning that the reaction rate depends on the concentration of both the nucleophile and the alkyl halide. As the slow step or rate-determining step involves two molecules, the mechanism is termed as bimolecular. This reaction occurs in a single step and does not involve any intermediate. Take note of the three-dimensional arrangement of the atoms around the carbon in the alkyl halide. The solid wedge is used to show the bonds coming out of the plane of the screen. The dashed lines show bonds going down the plane of the screen, while the straight lines represent the bonds in the plane of the screen. In the SN2 mechanism, the nucleophile attacks from the back of the molecule on the opposite side from the halogen atom, the leaving group in this reaction. The leaving group leaves simultaneously. This is described as a concerted mechanism. That is a one-step mechanism, because the new bond between the nucleophile and the carbon atom forms at the same time as that of the carbon-halogen bond breaks, as shown in the pentacoordinate transition state. Since the carbon atom is bonded to 5 atoms, the transition state is unstable and hence cannot be isolated. As the bond between the nucleophile and the carbon atom forms, the bond between the carbon and the leaving group weakens. The nucleophile essentially pushes the leaving group off the carbon atom. There is only one type of product in an SN2 reaction. If you compare the alkyl halide reactant and the substituted product, you can see that they have opposite stereochemistry. This switch is called an inversion of configuration. Can you imagine an umbrella being pushed inside out by a heavy wind? This is a useful analogy for understanding the SN2 mechanism. Let's apply our knowledge of nucleophilic substitution reactions to a couple of problems. Try to answer them on your own before checking the solutions. What happens when 2-bromo-octane is treated with aqueous potassium hydroxide? Start by writing out the reactants. The hydroxide ion is the nucleophile. See how it approaches the carbon atom from behind. Notice the inversion of configuration as the hydroxide ion pushes the bromide ion out to make 2-octanol. What happens when methyl chloride is treated with potassium cyanide? KCN is ionic, so it generates a cyanide ion which attacks the carbon in the methyl cyanide. In principle, the cyanide ion is ambident and could attack from either end. However, the CC bond is more stable than the CN bond. So, methyl cyanide is the primary product. If we wanted to make methyl isocyanide as the primary product, we should have used silver cyanide as the nucleophile. Since silver cyanide has significant covalent character, linking through the nitrogen atom predominates. As you've seen, the reaction involves the approach of the nucleophile to the carbon bearing the leaving group. Hence, the presence of bulky groups on or near the carbon atom will hinder the approaching nucleophile. Thus, among the alkyl halides, methyl halides, due to the presence of only 3 small hydrogen atoms, are the most reactive in SN2 reactions. Tertiary alkyl halides, on the other hand, due to the presence of bulky groups, are the least reactive in SN2 reactions. Thus, the order of reactivity of alkyl halides towards SN2 reactions is as shown here. Not all leaving groups react equally well. In general, among the halogens, fluorides are the poorest leaving groups, and iodides are the best leaving groups. In these pairs of halogen compounds, which would undergo an SN2 reaction faster? Let's start by drawing out the structures. For the first pair, 1-bromohexane is a primary alkyl halide, and cyclohexyl bromide is a secondary alkyl halide. We expect 1-bromohexane, then, to be more reactive and react more quickly. For the second pair, both structures are secondary haloalkanes. However, iodine has a weaker bond to carbon than chlorine. Alkyl iodides are much more reactive than alkyl chlorides. Now, it's time to turn our attention to the other mechanism called the SN1 reaction mechanism. The reaction between 3-bromo-3-methylhexane and hydroxide ion to yield 3-methyl-3-hexanol can be taken as an example of an SN1 reaction. The reaction shows first-order kinetics, as the reaction rate depends only on the concentration of the alkyl halide and not on the concentration of the hydroxide ion. The reaction occurs in 2 steps. In step 1, the leaving group departs, resulting in the formation of a carbocation. This step is slow and reversible. In step 2, the nucleophile attacks the carbocation, forming a covalent bond. The greater the possibility of the formation of a carbocation by an alkyl halide, the higher are the chances for the reaction to proceed via the SN1 mechanism. Further, the greater the stability of carbocation, the greater will be its ease of formation from alkyl halide, and the faster will be the rate of reaction. Thus, due to the greater stability of tertiary carbocations, tertiary alkyl halides readily undergo SN1 reactions. Allylic and benzylic halides also show high reactivity towards the SN1 reaction. This is because the allylic and benzylic carbocations formed get stabilized through resonance, as shown here. SN1 reactions are usually carried out in polar protic solvents such as water, alcohols, and acetic acid. The proton from the solvent molecules solvate the halide ion as it leaves in the first step of the mechanism. In the SN1 mechanism, there are two directions from which the nucleophile can attack the carbocation. Two different products can be formed from the SN1 mechanism. Compare the product that is formed when the nucleophile approaches from the left compared to when the nucleophile approaches from the right. They have the same formula, but different arrangements in space. These two products are mirror images of each other. They are not superimposable. Even if we rotate the right-hand molecule around the bond between the black and blue atoms, it still doesn't match the left-hand molecule. We call these as enantiomers. In the SN1 mechanism, both enantiomers are equally likely to form. This is called racemization, and such 50-50 mixtures are called racemic mixtures. You learn more about terms such as enantiomers and racemic mixtures, as well as about the stereochemical aspects of nucleophilic substitution reactions in the next module. You already know that an SN1 reaction proceeds with a complete racemization, while an SN2 reaction proceeds with a complete inversion. Why? In order to understand these concepts, we need to learn some elementary concepts of stereochemical principles and notations, such as plane polarized light, asymmetry, chirality, racemization, inversion of configuration, and retention of configuration. Let's start our discussion with plane polarized light and optical activity. Ordinary light is light vibrating in all directions through the line of propagation. When ordinary light is passed through a lens made of Polaroid, or more traditionally calcite, it produces a light that vibrates in only one plane and is called plane polarized light. When plane polarized light is passed through a solution of certain compounds, they rotate the plane polarized light in a specific direction. Such compounds are called optically active compounds. Let us see how this rotation of the plane of polarized light or optical activity can be detected. The angle by which plane polarized light is rotated is measured by an instrument called a polarimeter. It consists of a light source, two lenses, and a tube between the lenses to hold the substance that is being examined for optical activity. This arrangement is schematically represented as shown here. If a substance rotates plane polarized light to the right or clockwise, as seen by an observer towards whom the light is approaching, then it is called dextro-rotatory or D form. It is indicated by placing a plus sign before the degree of rotation. In Greek, dextro means right rotating, and hence the term dextro-rotatory. On the other hand, if a substance rotates plane polarized light to the left angle or counterclockwise direction, as seen by an observer towards whom the light is approaching, then the compound is said to be levorotatory or L form. It is indicated by placing a minus sign before the degree of rotation. In Greek, levo means left rotating, and hence the term levorotatory. For example, the lactic acid extracted from muscle tissue rotates plane polarized light to the right, and hence is known as dextro-rotatory lactic acid or plus lactic acid. Similarly, the 2-methyl-1-butanol obtained from fusel oil rotates plane polarized light to the left, and it is known as levorotatory 2-methyl-1-butanol or minus 2-methyl-1-butanol. Such plus or minus isomers of a compound are called optical isomers, and the phenomenon is known as optical isomerism. According to Louis Pasteur, a noted scientist, the optical activity of a compound is associated with the three-dimensional arrangement of atoms in a molecule. The two forms of crystals of certain compounds in their aqueous solutions show optical rotation, equal in magnitude but opposite in direction. He concluded that the difference in optical activity is due to the difference in the three-dimensional arrangement of atoms in the two types of crystals. Later, a Dutch scientist, J. van 't Hoff, and a French scientist, C. Hebbal, independently argued that if all the four substituents or groups attached to the central carbon atom are different, then such a carbon is said to be an asymmetric carbon or stereocenter. The resulting molecule is said to be an asymmetric molecule. This asymmetry of the molecule is responsible for optical activity. You see symmetry and asymmetry commonly in your everyday life. For example, a sphere, a cone, and a cube are identical to their mirror images and are superimposable. However, many objects are non-superimposable on their mirror images. For example, the left hand and the right hand are mirror images of each other, but they do not superimpose, and hence are said to be non-superimposable. Objects that are non-superimposable on their mirror images are said to be chiral, and this property is known as chirality. On the other hand, objects that are superimposable on their mirror images are called achiral. Let us apply this concept to organic molecules. Chiral molecules may contain one or more asymmetric carbons or stereocenters. An asymmetric carbon is represented with a star on it. Consider two simple molecules, propan-2-ol and butan-2-ol, and their mirror images as shown here. Propan-2-ol does not contain an asymmetric center, since the four groups attached to the tetrahedral carbon are not all different. Thus, it is an alkyl. However, butan-2-ol contains four different groups attached to the tetrahedral carbon. Hence, it is an asymmetric molecule and is expected to be chiral and optically active. Some common examples of chiral molecules are 2-chlorobutane, 2,3-dihydroxypropanol, lactic acid and mandelic acid. Non-superimposable mirror image isomers are known as enantiomers. Enantiomers possess identical physical properties like melting points, boiling points, solubility, and refractive index. They only differ with respect to the direction of rotation of plane polarized light. They can either be dextrorotatory or levorotatory. If a mixture contains equimolar proportions of enantiomers, then it shows zero optical rotation. Such a mixture is known as racemic modification. A racemic mixture is represented with the symbol Dl or plus minus before the name of the compound. The process of the formation of an equimolar proportion of an enantiomeric mixture from an optically pure compound is known as racemization. Another important concept is that of retention and inversion of configuration. Retention of configuration is the preservation of the integrity of the spatial arrangement of bonds to an asymmetric center during a chemical transformation. For example, in the conversion of a chemical species XCABC to YCABC, the relative configuration of the reactant XCABC is retained in the product. In general, if there is no detachment of the bond attached to the stereocenter in the chemical transformation, then the product will have the same configuration of the groups around the stereocenter as that of the reactant or the substrate. Such a reaction is said to proceed with retention of configuration. In the reaction that takes place when -2-methylbutan-1-ol is heated with concentrated hydrochloric acid, there is retention of configuration as shown here. Inversion of configuration in a reaction yields a product whose configuration is opposite to that of the reactant or the substrate. For example, when -2-bromooctane reacts with sodium hydroxide in a reaction that follows second-order kinetics, +2-octanol with inverted configuration is obtained. You are already familiar with the reaction mechanism of nucleophilic substitution reactions of alkyl halides. An SN1 reaction is accompanied by racemization, while an SN2 reaction proceeds with inversion of configuration. Can you think why? we can illustrate the stereochemical aspects by taking the example of an optically active alkyl halide as a substrate. In this process, if the reaction conditions are favorable for first-order kinetics, then it follows the mechanism of an SN1 reaction. This mechanism proceeds in two steps. In the first step, which is the slow step, the alkyl halide undergoes ionization and forms a stable carbocation intermediate. This intermediate is sp2 hybridized and has a planar geometry as shown here. In the second step, the attack of the nucleophile on the planar carbocation intermediate can take place from either face with equal ease. This results in the formation of a mixture of products in equal quantities, and this process is known as racemization. In one of these products, there is inversion of configuration, while in the other, the configuration is retained. Thus, the SN1 mechanism is accompanied by racemization. It is clear that the formation of the inversion product is due to the attack of the nucleophile on the planar carbocation intermediate from the side opposite to that of the leaving group. On the other hand, the formation of the retention product is due to the attack of the nucleophile on the planar carbocation from the side same as that of the leaving group. An example of this type of reaction is the hydrolysis of optically active -2-bromobutane yields a mixture of plus and -2-butanol. Remember that it's a racemization process. Now, if the reaction conditions are extremely favorable for second-order kinetics, then the alkyl halides follow the SN2 reaction mechanism. It's a concerted process. That is, it proceeds in a single step. Here, the nucleophile attacks from the direction opposite to that of the leaving group, which is also known as a backside attack. In this process, the displacement of the leaving group from the carbon atom of the substrate and the formation of a new bond with the nucleophile take place simultaneously. This results in an unstable transition state with 5 bonds. These bonds in transition state are distorted from the tetrahedral geometry of an alkyl halide. They exist as a planar spoke arrangement for a short time. Then, the leaving group is expelled and results in a product with a complete inversion of configuration. This is known as umbrella inversion. Thus, the SN2 mechanism is accompanied by a complete inversion of configuration. An example is the reaction of -2-bromooctane with sodium hydroxide to form plus octane 2-ol with a complete inversion of configuration. You will learn about elimination reactions of haloalkanes and also their reactions with metals. Apart from undergoing substitution reactions, haloalkanes also undergo elimination reactions. In these reactions, a haloalkane with a beta hydrogen atom, on heating with an alcoholic solution of potassium hydroxide, loses a halogen atom from the alpha carbon and a hydrogen atom from the beta carbon to form an alkene molecule. Since a beta hydrogen atom is involved in the elimination, these reactions are often called beta elimination reactions. What if there is more than one beta hydrogen in the molecule? In this situation, more than one possible product can be formed. In such cases, the major product can be predicted by Zaitsev's rule or Zaitsev's rule. According to this rule, in dehydrohalogenation reactions, the preferred product is the alkene that has the greater number of alkyl groups attached to the doubly bonded carbon atoms. Let's look at an example. Looking at the reactant molecule, we see that there are two beta carbons, one on either side of the carbon attached to the chlorine atom. We could remove a hydrogen atom from either beta carbon, leading to two possible products. When we draw the structure of the two products, we see that the first product, formed when a hydrogen atom is removed from the left beta carbon, has three alkyl groups linked to the carbons of the double bond. The second product, formed when a hydrogen atom is removed from the right beta carbon, has only two alkyl groups attached to the carbons of the double bond. Thus, according to Zaitsev's rule, the first product is the preferred product. Now try a problem on your own. Predict the alkenes that would be formed by the reaction of 2-chloro-2-methyl-butane with sodium ethoxide in ethanol. Sodium ethoxide in ethanol is a strong base. Try to work out the answer independently before checking the solution. How can dehydrohalogenation by beta elimination occur in this molecule? The chlorine atom can be removed from carbon number 2. But from the structure, we see that there is a choice of two positions from which a hydrogen could be lost. Two products will form. Zaitsev's rule predicts which alkene is formed in the greatest amount. 2-methyl-2-butene has three alkyl substituents of the double bond. In comparison, 2-methyl-1-butene is disubstituted. Therefore, Zaitsev's rule predicts that 2-methyl-2-butene is the major product. An alkyl halide may either undergo substitution or elimination reaction depending on its nature and on the strength and size of the nucleophile. In the presence of a bulkier nucleophile, elimination is preferred over substitution. Due to the steric factors, the abstraction of proton is comparatively easy than approaching the tetravalent carbon for substitution. For example, primary alkyl halides have little steric hindrance, and hence readily undergo SN2 reactions, while tertiary alkyl halides undergo SN1 reactions due to the formation of a stable carbocation. Secondary alkyl halides, depending on the strength of the base or nucleophile, may undergo either substitution or elimination reactions. Now let us look at the reactions of haloalkanes with metals. Most organic chlorides, bromides, and iodides will react with certain metals to form compounds containing carbon-metal bonds. Such compounds are called organometallic compounds. We will discuss two classes of reactions of alkyl halides with metals. One important class of organometallic compounds is called Grignard reagents. Grignard reagents are alkyl magnesium halides. They have the general formula RMgX, where R is an alkyl or aryl group and X is a chloride, bromide or iodide. A Grignard reagent can be synthesized by combining a haloalkane with magnesium metal in dry ether. A general equation is shown here. Grignard reagents are used in a variety of organic syntheses. For example, bromomethane reacts with magnesium in dry ether to form a Grignard reagent. Methyl magnesium bromide. In a Grignard reagent, the carbon-magnesium bond is covalent but very polar, with the carbon being more electronegative than magnesium. The magnesium-halogen bond is essentially ionic in nature. Grignard reagents are highly reactive compounds. They react with any source of proton, even with weak proton donors, such as water, alcohol or amines, to give hydrocarbons. The reactions of Grignard reagents with water, alcohol and amines to form alkanes are shown here. This is one of the methods to convert alkyl halides into hydrocarbons. Since Grignard reagents readily react with water, it is very important to prevent them from coming in contact with even traces of moisture. Here's a problem for you to try. What happens when bromocyclohexane is treated with magnesium in dry ether? What will form if this product is then reacted with water? You should recognize that a Grignard reagent will be formed under these conditions. The Grignard reagent is shown in the first equation. Then, if water is present, the Grignard reagent will react to form cyclohexane. One of the oldest organic synthesis reactions is called the Wurtz reaction. Alkyl halides react with sodium in dry ether to make a new carbon-carbon bond, as shown in the general equation. The Wurtz reaction works best to make symmetric alkanes. Polyhalogen compounds are carbon compounds containing more than one halogen atom. Some examples of polyhalogen compounds are shown here. Many polyhalogen compounds are useful in the industry and in agriculture. Dichloromethane, also called methylene chloride, is a colorless volatile liquid with a moderately sweet aroma. Dichloromethane is used as a propellant in aerosols and also as a paint remover. However, the use of dichloromethane for removing paint has been banned by the European Union since it is a carcinogen or a cancer-causing agent. Dichloromethane is also used as a process solvent in the manufacture of drugs. It has additional uses as a metal cleaning and finishing solvent. There are some very real human health risks associated with exposure to dichloromethane. It harms the central nervous system. Exposure to even low levels in the air can lead to slightly impaired hearing and vision. Exposure to higher levels in the air may cause dizziness, nausea, and tingling or numbness in the fingers and toes. The skin may experience an intense burning sensation and mild redness if it comes in direct contact with dichloromethane. If dichloromethane comes in direct contact with the eyes, it may burn the cornea. Trichloromethane, or chloroform, is a colorless, volatile, non-flammable liquid with a sweet odor. It is used as a solvent for fats, alkaloids, iodine, and other substances. It is also used in the synthesis of freon, a refrigerant, or R22 shown here. Many nations are phasing out the use of R22 due to concerns about its role in ozone depletion. Chloroform was once used as a general anesthetic in surgery. However, this use has been discontinued as there are a number of safer alternatives. Exposure to chloroform can cause serious problems to human health. Breathing in chloroform vapors depresses the central nervous system. Not surprising, considering its historical role in anesthesia. Breathing chloroform about 900 parts per million, even for a short time, can cause dizziness, fatigue, and headache. Chronic chloroform exposure may cause damage to the kidneys and liver. In the liver, chloroform is metabolized to form phosgene, a deadly gas. We'll discuss phosgene in greater detail shortly. Some people will develop sores if the skin comes in contact with chloroform. Chloroform is slowly oxidized by air in the presence of light into deadly phosgene gas, as shown in the reaction. Therefore, chloroform is stored in dark bottles to prevent exposure to light. The bottles are filled completely to keep air out. For the sake of safety, handle every bottle of chloroform as if it contains phosgene. Wear gloves and eye protection. There are simple tests that you can carry out to determine the presence of phosgene. Phosgene, or carbonyl chloride, has a characteristic odor of cut hay. It is highly toxic. In fact, it was used as a chemical warfare agent during the First World War. If you detect the odor of freshly cut hay when working with chloroform, you should seek medical attention. Chloroform contaminated by phosgene should not be used and should be properly disposed of as chemical waste. Triiodomethane, or iodoform, is a pale yellow crystalline solid. This volatile compound has a pungent, medicine-like odor. Iodoform has uses as an antiseptic. Gauze packing with iodoform is used in medical applications. However, the antiseptic properties are due to the liberation of free iodine, not the triiodomethane molecule itself. Due to iodoform's penetrating odor, other antiseptics are used more commonly. Carbon tetrachloride, or tetrachloromethane, is a clear liquid with a sweet smell. Carbon tetrachloride has a variety of uses, including in the manufacture of refrigerants and aerosol propellants. It is used in the synthesis of chlorofluorocarbons. It is widely used as a solvent. Due to safety concerns, many chemists prefer to use other solvents. In the past, carbon tetrachloride was used as a dry cleaning fluid, a degreasing agent and spot remover, and also as a fire extinguisher. These uses have been generally phased out to minimize health risks. The health risks associated with carbon tetrachloride are very serious, as the substance is a suspected carcinogen. Chronic exposure to carbon tetrachloride may cause liver cancer in humans. Kidney damage is also a risk. The side effects of exposure to carbon tetrachloride include dizziness, lightheadedness, nausea, and vomiting. It causes eye irritation and may lead to an irregular or stopped heartbeat. Continued exposure can lead to unconsciousness, coma, or even death. Carbon tetrachloride has been linked to the depletion of the ozone layer. Depletion of the ozone layer increases our exposure to ultraviolet light, leading to a higher risk of skin cancer, eye diseases, and disorders, and possible disruption of the immune system. Freon is the name given to a class of compounds that are chlorofluorocarbon derivatives of methane and ethane. These compounds are extremely stable and unreactive. They are non-toxic, non-corrosive, and easily liquefiable gases. Freon 12, illustrated here, was one of the most commonly used freons in the industry. It is manufactured from carbon tetrachloride by the Schwarz reaction. Former uses of Freon 12 included aerosol propellants, refrigeration, and air conditioning. Since 1994, the use of Freon 12 is being phased out according to the Montreal Protocol due to environmental concerns. Freon 12 and other chlorofluorocarbons are known to initiate radical chain reactions that lead to the destruction of the ozone layer. The final compound that we'll discuss is known as DDT. Paul Mueller was awarded the Nobel Prize in Physiology and Medicine in 1948 for his discovery that DDT could be used as an insecticide. DDT has been used to prevent insect-transmitted human diseases such as malaria, spread by mosquitoes, and typhus, spread by lice. However, many insect species develop resistance to DDT, limiting its effectiveness. DDT is toxic to many species of fish. For certain species of birds, such as ospreys, eagles, pelicans, falcons, and hawks, DDT exposure leads to thinning of eggshells, causing serious population declines. DDT is stored in the fatty tissue of the body and is metabolized very slowly. As a result, it persists in animals and becomes more concentrated in species higher in the food chain. The use of DDT in agriculture has led to measurable DDT levels in humans. The use of DDT was banned in the United States in 1973. However, it is still in use in some parts of the world.